Hello everybody, myself Prashant Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. In the last class of Electric Machine 2, so we have discussed about the equivalent circuit and phasor diagram of synchronous generators. So today actually we'll discuss a numerical example of equivalent circuit, and then we'll discuss about the armature reactions of the synchronous generator thereafter. So let us start with the example of a for equivalent circuit. So example is like this: 200 kVA, 480 volt, 50 hertz. Star connected synchronous generator with a rated field current of 5 ampere was tested, and the following data were obtained. So terminal voltage at open circuit VT OC, that is open circuit voltage particularly 540 volt at the rated field current IF, and second is given with the short circuit line current IL/ISC, that is equal to 300 ampere at the rated field current IF. And third point is when a DC voltage of 10 volt was applied to two of the terminals, a current of 25 ampere was measured. So this is the data given, and you have to find out the generator's model and the rated conditions. So generator model means you have to find out the armature resistance and the approximate synchronous reactance. Okay. So once again, actually, I am repeating the example of 200 kVA, 480 volt, 50 hertz star connected synchronous generator with a rated field current of 5 ampere was tested, and the following data was obtained. Terminal voltage at open circuit conditions as 540 volt at rated IF, that is at 5 ampere, and rated line current at short circuit condition is 300 ampere at rated IF, again it is 5 ampere, and when DC voltage of 10 volt was applied to two of the terminals, a current of 25 ampere was measured. To find the generator's model at the rated condition, and that is armature resistance and the approximate synchronous reactance. So this is the problem given. So since this generator is a star connected, DC voltage was applied. So this is a star connected generator. So these are the armature resistances. So if a DC voltage is applied from any between its two phases, so that is so DC voltage of 10 volt is given, and as a result, 20 ampere current is flowing. So if we see. So this will be actually this RA plus RA. 2 RA should be equal to how much? 10 by 25. The VDC by IDC. So this will be how much? 2 into actually this will be 10 by this is 2 into 25 2 ID. So it is actually 0.2 ohm. Okay, this is actually armature resistance. Okay, now internal generated voltage at a rated field current is how much? This is actually this internal generated voltage. This is VT by root 3. That is 540 by root 3. The 540 is given here. Yeah, VTOC. So it is actually 311.8 volt. 311.8 volt, and the synchronous reactance at the rated field current is precisely x is equal to root over of z square minus ra square. So that is equal to a by isc the whole square, so minus ra square. So it is actually 3.11.8 whole square by 300 square. That is 300 is given here. If you see, this is the 300. Okay, so that means it is coming to 1.02 ohm. Okay, so we observed that if synchronous reactance was estimated via the approximate formula, the result would be X is equal to A by ISC, that is 311.8 by 300, that is 1.04 ohm. So almost same. So it is close to the previous result. And the error ignoring RA is much smaller than the error due to of course saturation. Okay. So this is actually equivalent circuit. So this is 0.2 ohm armature resistance, and this is the reactance. So that is equal to 1.02 ohm. And this is actually to be precise enough 3.11.8 volts. So actually T12 at the angle of delta load angle or torque angle. So at delta, this is actually between the angle between the A and the phi actually. So this is the phi. Okay. So this is equivalent circuit. Clear? So actually that is actually about this so problems on an equivalent circuit which we have say discussed in our last class. So actually this is the problem. Next we will start armature reaction. So now we will discuss armature reactions in alternator or synchronous machines. So basically when armature winding in any electrical machine is the winding which carries the load current. So basically under no load conditions the armature current is zero, and but as the machine is loaded, load current flows to the armature winding and creates magnetic flux, which is basically known as the armature flux. So the effect of this armature winding MMF or flux on the main working flux created by the field poles, or that is the main flux or main is called the armature reaction. So armature reaction means when armature is loaded, basically when armature current is flowing to the armature conductor, so armature flux will be generated, and this armature flux will interact with the main flux which is created by the field winding, so that is field flux. And as a result, so the resultant flux condition will be something different. So that may be magnetizing, maybe demagnetizing, maybe say cross magnetizing, maybe both. So that totally depends on the nature of the load itself. So basically, so this in this lectures we'll actually discuss about this armature reactions in the synchronous machines or alternator. So to understand in a better way this armature reactions in a synchronous machine, it is necessary to first understand the internal happenings of the synchronous generators. And so for this first pass, alternator operation is considered under different operating power factor and loads, particularly depending on the load, power factors also will be changed. So first of all, we start with no load operations. So when armature is not loaded, then unity power factor load, that is the load, very nature of the load is resistive. Zero power factor load, so lagging load, and zero power factor leading load, and particularly more generally the load which we are we are finding in case of synchronous generator is the lagging power factor load. So let us start our discussions with no load conditions and what its effect on the armature reaction. So let's take no load operations. So in no load operations means there is no current flowing to the armatures. So since no current is flowing to the armatures, so there is no case of forming armature flux or armature MMF. So as a result, no question arising out of for armature reaction. So as a result, so only the field flux or the main flux will be there. So when the field winding is excited by DC source and the alternator generator is brought up to synchronous speed by adjusting the prime mover speed, no load voltage or excitation voltage is generated across the alternator armature terminals, and the value of no load or excitation armature terminals voltage, which we have already discussed in our in the equation of the EMF generated. So this is the RMS value of the excitation voltage, it will be root 2 pi f n phase kW phi f. So that is EF n phase kW and phi f are this is excitation voltage, this is the number of series turns per phase of the armature conductors, this is actually winding factors, and this is the flux per pole. Okay, so this generated excitation voltage across the armature terminal lags behind the field flux by 90 degree. That means if this is the flux, so field flux, so our induced EMF on the armature, that is excitation EMF, will be 90 degree out of phase, and it is lagging. Okay, 90 degree lagging. So this is the field flux, and this will be the armature, say armature induced EMF or excitation EMF. So mostly all the field flux always lags behind generated EMF by the field flux is always lags behind the field flux by 90 degree in all machines. So this is basically as per Faraday's law of electromagnetic induction. So E equal to minus d phi dt. So minus for lagging and d dt of phi means it is of 90 degree phase difference, out of 90 degree phase difference. Okay, so unity, now we'll talk about unity power factor load. Now, in order to understand the effect of armature MMF on the field web, so let us consider two-pole cylindrical rotor alternator. So understand it is better with for unity power factor load of the effect of armature MMF on field MMF web. So we are considering two-pole cylindrical rotor alternator. So here it is. So this is a two-pole machine. Okay. So basically, this is a rotor. This is rotor. This is stator. These are the stator winding. So basically, this is actually phase A. This is 120 degree apart of phase A. That is phase B. Okay, and this is phase C. Again 120 degree apart. So if you see like this is actually, if it is say coil A, so this is its axis of phase A, and this is actually the field. This is field winding. Okay, this is actually field, say axis of the field coil. So that actually axis of the field coil means this is the axis of the field flux or field MMF. Okay, so this is uniform air gap, and this is stator, and this is rotor. So this figure, so concentrated full pitch coils, as I told you, this A dash, B dash, or B prime, C dash on the stator. So this is A dash, so B dash, okay, and then C dash. Okay, so represent the three phases of the phase winding, say A, B, and C. And field winding on the rotor is fed by a DC source. So DC source of say setting up working or main field MMF. Okay, so this field winding on the rotor is fed by a DC source. So for setting up working on main field MMF. So field current indicated by cross and dot in the field winding. So this is actually the field current. Okay, this is by cross and dot in the field winding on the rotor, and here's the field MMF effect. Okay, and field flux phi f. Here, as you know, this MMF is and flux is actually flux is Ni by reluctance. So it's in reluctance, so this will be in the same phase. So, so this field current, the field MMF and field flux, which are sinusoidally distributed along the air gap periphery. So this field flux create a north and south poles on the rotor. So this will indicate north and south pole of the rotors. So these are the say north and south pole of the rotor. And as we know, this EMF induced in a coil is maximum when its coil sides are lying under the maximum flux positions. So in view of this maximum EMF will be generated in coil A as its coil sides A are lying under the peak flux density. This is actually okay. This generated EMF is shown by this dotted line. This is actually the generated EMF. Generated shown by dot and cross at A and A dash, basically A and A dash here, respectively, assuming anticlockwise rotation of the rotor, since coil sides B dash and C dash are also under the influence of B dash and C dash are also under the influence of the north pole, EMF induced in these coils are represented by a dot, and however their magnitude will be less than the maximum values. So this is shown here. Okay. So B dash and C dash under the north pole also. So there will be a dot, but their induced EMF will be less than the maximum values. So this EMF generated by field flux phi f alone is called the excitation voltage, or EF. Okay. So now when this alternator is connected to a balanced three-phase load, a balanced three-phase current starts flowing in the three phases of the alternator, and as the load is of unity power factor, that means the field excitation voltage EF and the armature current IA will be in phase. So basically this will be in the same direction, that is induced EMF and the armature current. Okay, so this can also be interpreted that in another way, that like excitation voltage and armature current attain their peak simultaneously, and since the excitation voltage is maximum in phase A, this armature current phase A will also be maximum. So, though the load current also flows in the remaining two phases B and C, but their magnitude is less than the maximum at the instant of time. The MMF set up by the armature current is called the armature reaction MMF, and as we know that for balanced polyphase currents flowing in the polyphase winding, the peak value of the resultant MMF wave is along that phase axis, which carries the maximum current. So therefore, the resultant armature reaction MMF due to combined effect of three-phase MMF is set up along the phase A, because the phase A carries the maximum current. So this is actually shown here. So this is actually armature current, say unity power factor load. So this is armature current, and excitation EMF will be on the same phase. So as a result, this is the armature MMF, and along this direction, armature flux will be generated, and the resultant of these two MMF, this is field MMF and the armature MMF, will give the resultant MMF FR. Okay. So this is shown here. This is actually maximum armature current coil. These are the less armature current carrying coils, B dash and C dash, under the north pole. So armature reaction produces north and south poles on the stator. This north and south pole on the stator. So this actually. Okay. So the interaction between these poles on stator and the rotor causes the production of electromagnetic torque, and for an alternator, the prime mover torque must counteract this electromagnetic torque for conversion of mechanical energy into electrical energy. So this is actually the say rotor pole, and this is actually the stator pole, magnetic poles, so armature poles actually. So and this is main field pole. So the interaction of these two will create the say torque, and this must be counteract with the prime mover torque, and as a result also power conversion of mechanical engine to electric usually happen. So if we combine the space phasor and the time phasor, that is space phasor of field EMF and armature EMF wave, and with time phasors of the EMF and armature current, so we will get the combined phasor diagram of this situations of the armature reaction. So basically, this is actually field MMF. This is armature MMF. This will give you the resultant MMF, and this is the resultant flux. So the resultant air gap MMF must be this resultant of this FA plus say FF. And if we neglect the saturation, then the field flux and the armature flux will be along their respective MMF wave. So this is shown here. This is actually, and thus we can say the armature reaction flux lags behind the field flux by 90 degree. Okay, this is armature reaction flux, and this is field flux by 90 degree. And therefore, the armature reaction MMF at unity power factor is entirely cross magnetizing in nature. Okay, so from here we are finding this is cross magnetizing in nature. Now we'll discuss zero power factor lagging load. So zero power factor lagging load means load current is lagging behind the excitation voltage by 90 degree, and this is shown here. So this is actually excitation voltage, and this is the load current. So armature current which is lagging behind this excitation voltage by 90 degree. Basically, this is the time phasors, and this is the space phasor. Actually, this MMF, field MMF, and the flux MMF. So this is the combined figure of zero power factor lagging load armature reactions phasor diagram. So in this figure, actually, this is axis of the field, and this is the rotations of the rotor. So actually, this phasor diagram has been done using the following facts. So the excitation EMF lags behind the field MMF by 90 degree. This is excitation EMF and lagging behind the field MMF or field flux by 90 degree. And saturation is neglected. The field flux will be along the field MMF since saturation has been neglected. So this phi F and FF will be is in the same phase. Armature reaction MMF is along the armature current. So this is armature current which is lagging behind the excitation EMF by 90 degree. So this is armature current. So this will be the armature MMF flux. That's MMF. So FA, and armature reaction MMF is of course is along the armature current. Okay. So since from this phasor diagram we are finding that the armature reaction MMF FA is in opposition with the field MMF actually FF. So this is actually FF. This is field MMF flux. So this is actually will be FF. So this means that the resultant air gap MMF will be equal to. So resultant MMF will be equal to say FF minus FA. So this is resultant. Okay. So this under zero power factor lagging load condition, the alternator of the effect of the armature reaction MMF is purely demagnetizing. See, so this is actually armature reaction MMF which is opposing this field MMF, and as a result the resultant MMF has been reduced by this amount. Okay. So this is demagnetizing in nature, purely demagnetizing in nature. So this can be understood in any another way that is also described here. So due to zero power factor lagging load, the current in phase A, the current in phase A winding will become maximum armature current, and when the field poles are in poles have advanced by 90 degree. So this is advanced by 90 degree. So basically this is shown here. So if you compare the earlier one, actually here it is. This is actually the positions of the field poles. So this is N and this is S actually, and here it is like this. So it is advanced by 90 degree. Okay. Previously it was here. Now it is here. So it is advanced by 90 degree. So actually, if we observe these figures, it can be seen that in that case, reaction, armature reaction, MMF FA will be along the phase A axis. Will be along the phase A axis, and that of the field. Actually, this will be the field, not field. FI field MMF. Sorry. No. So field MMF. This is actually field. So field MMF will be vertically downward. Okay. So FA will be along the axis of the phase A, that is upward, and field MMF FF will be vertically downward. Here, that will be vertically downward. Okay. So as a result, this direction can be found by using right hand Scott screw rule also. So thus we see that both the armature reactions and this armature reactions and field MMF are opposing each other. Hence the effect is of armature reaction MMF is purely demagnetizing in zero power factor lagging load conditions. And for so this is also shown here. So for zero power factor leading load, basically the condition zero power factor leading load may be depicted by this phasor diagram. This is excited EMF. So leading, so IA is 90 degree leading, purely. So this is zero power factor leading load. So the zero power factor lagging load that we have done. So this is zero power factor lagging. So what will happen? So this is the armature MMF, and this is if we this is armature reaction, this is armature flux. So as a result, so this resultant flux will be this plus this. So this will be enhanced or increased. So that is actually magnetizing effect. So that the armature reaction MMF is in the direction of the field MMF, and the effect of the armature reaction MMF under zero power factor leading load is purely magnetizing. So again, this can be analyzing by space phasor of the alternator. So if we take the space phasor of the alternator, so zero power factor leading means the current in phase A of the armature winding will be 0 when the field poles are behind the axis of the phase A winding by 90 degree as shown in this figure. So this is actually field MMF and this is FA. So the resultant MMF will be more. So therefore the reactions of the field MMF and the armature MMF will be the same. Hence armature reaction MMF is magnetizing in nature. Okay. And lagging power factor load, if we consider the lagging power factor load, so we consider the general case of the armature current IA lagging the excitation EMF by angle theta. So this means that the load power factor is cos theta. So for a lagging power factor load having power factor angle theta, the current coil and A and A dash will be maximum when the field poles have advanced by 90 degree in space. In other words, by the time armature current in a coil A A dash attains a maximum value with the same polarity. Dot in the coil side A. So rotor poles N and S would have moved forward by 90 by theta degree, as in this figure below. So this is actually the case. This is actually field MMF. Okay. Actually, in this direction, this is A dash. This is actually armature flux. So this will be this is the resultant. This is resultant MMF. So if we see this phasor, so this is actually field phasor, field MMF, armature MMF. This is resultant MMF. This is field flux. This is armature flux. This is resultant flux, and this is excitation MMF. So resultant of rotating armature MMF FA is directed vertically upward along the axis of the phase A, because this phase carries the maximum current at the instant to consider, and thus the armature reaction MMF FA is lagging behind the field MMF FA by 90 plus theta degree. So let us now draw the phasor diagram like this. So this is actually field MMF, this is lagging power factor armature current, this is armature MMF, this is armature flux, and as a result this is the resultant MMF, or this is field flux, this is armature flux, and this is resultant flux. So this is excitation EMF, this is excessive EMF. So actually this component in two, one is the cross magnetizing effect and another is the demagnetizing effect. Okay, Fa cos theta is for cross magnetizing effect, and this is Fa sin theta of this armature MMF is demagnetizing, having demagnetizing effect. So the armature reaction MMF can be dissolved into two components, one along the excitation voltage Fa cos theta and another opposite to the field MMF Fa sin theta. So thus we can see that the effect of armature reaction in lagging power factor load is cross magnetizing as well as demagnetizing in nature. So just to summarize the effect of the armature reaction MMF on the main field MMF of alternator, it is tabulated here. So in the loading condition, no load effect is armature reaction has no effect. Unity power factor loading condition, cross magnetizing effect, and zero power factor lagging, purely demagnetizing, zero power factor leading, purely magnetizing, and lagging load, both cross magnetizing and demagnetizing effect. So that's all about the armature reaction. So from this we are getting the armature reactions on the of the synchronous generators and its effect at different conditions, loading conditions, no load, unity power factor load, zero power factor lagging, zero power factor leading and lagging load. And we have this effect of respectively like no load, it's no effect, unity power factor having cross magnetizing effect, and zero power factor lagging load having purely demagnetizing effect, and zero power factor leading purely magnetizing effect, and lagging load having cross magnetizing and demagnetizing both effect. So we have discussed this on the basis of this assumption. This we have drawn the space phasors taking all the MMF, that is main MMF or field MMF and armature MMF, and then resultant MMF, and then we have drawn the excitation EMF and armature current on say time phasors, and when these two phasors are combined, we'll get the combined effect will give the phasors of armature reactions of synchronous machine. Okay, so I think you have so you understand everything about this armature reaction, and if you don't understand it, or if you have any problem, so with it, listening this video lectures, you must follow or go to your textbook carefully. That is the most of this armature reaction part I have taken from the electrical machinery of P.S. Bhimra. So if you go to that book also, what I am telling today in this armature reaction portions will be clear for you. And after that, if you have any queries, you may ask me, and definitely we'll discuss the problem whatever you are facing with this. So in a nutshell, I have talked this armature reaction of the synchronous machines to you. So hope you will understand it, and you have understood it. Okay, thank you for present here.